We are now going to talk about out-of-sample validation, which is critical in assessing a model's ability to make good predictions. It is actually at the core of machine learning, and it explains why these machine learning models are so good at predicting. Why do we want to validate the model out of sample? Well, if you use only in-sample fit statistics, like R-squared or adjusted R-squared, you might not have an accurate representation of how well your model will be at predicting new observations that were not in your sample. It will likely overestimate the ability of the model to make accurate predictions. This happens whenever two variables are correlated in your sample simply by chance, and the more you add variables in the model, the more likely you are to find variables that are just correlated by chance. And it also happens when your model is too flexible and overfits the data in your sample. This is what happens on the right. You can see that the model, represented by the yellow curve, can predict almost perfectly all the observations in the sample. If you have an R-square of nearly 1, like is the case here, you can suspect overfitting. It's saying that it can explain nearly all the variations in Y with the model. But if you add new data points, do you think they would fall close to the curve? Well, I excluded some of the data points from the regression, and I can see if the model is good at predicting them. You can see here that the model is actually pretty bad at it. This is exactly what out-of-sample validation does, and it is a good way to assess the ability of a model to predict new points. In the current era where data is widely available, we usually have enough data to perform the regression and the validation on different samples. So you should use out-of-sample validation as much as you can. This is why machine learning also could become so popular. We have so much data now that we can use out-of-sample validation easily. The out-of-sample model validation process is fairly simple. First, you take your dataset and you randomly partition all the observations into two sets. The first set is called the estimation set, or the training set if you're doing machine learning, and the validation set. Then you just use the estimation set to estimate the parameter, so you fit your regression to the estimation set. Then, instead of predicting the observation in the estimation set, you use your estimated parameters to predict the observation in the validation set, so the observations that were not used to fit the regression. You calculate the residuals in this validation set by subtracting the actual value with the predicted value, and you calculate the prediction errors. And we are going to see that there are different measures to calculate the prediction error. Here are three common and useful measures of prediction error. All three are a function of the model's residuals, so the observed minus the predicted value of the dependent variable. You could actually use them in sample by using the residuals from the training set, but if your goal is to measure the model's ability to predict new observations, the best is to use the validation set instead. The three measures tend to move together but have slightly different interpretations. We have the mean absolute error, MAE. We have the mean absolute percentage error, MAPE. And then the root mean squared error, or RMSE. The MAE is how wrong the model is on average in terms of the units of Y. For instance, you could say the model is wrong by $4 on average. The MAPE is similar but can be interpreted as how wrong the model is on average in terms of percentage. In this case, you would say the model is wrong by 3%. Instead of units, you use percent on average. Finally, the RMSE is also in terms of units, so not percent, but because of the square, it is greatly affected by outliers. So you should use it if a few large prediction errors might have a substantial impact on your business. The formulas are easy to remember because they match the names. So if you look at the mean absolute error, you can see that we have yi minus y hat, that's the error. And then we take the absolute value to get the magnitude of the error, and then we take the average of that. So we have the mean of the absolute value of the error, hence mean absolute error. Then similarly, for the mean absolute percentage error, we have the residual again, so the error, yi minus y hat, but it's divided by yi, sorry. So it's in terms of percentage. So if the error is $1, but yi is $100, then the error is 1%. Then you take the absolute value, and then you take the mean of that. So you have the mean of the absolute value of the error in terms of a percentage. Finally, we have the root mean square error. And then again, we take the error, we square it, we take the mean of that, and finally, we take the root to bring it back into units instead of squared units. So we have the root of the average of the squared of the error. Hence, root mean squared error.